On this lesson, we're going to do some practice problems whenever we're trying to convert equations for polar to rectangular and vice versa. So we'll start by just remembering that these are the expressions that we use for this task. We have shown that any x value, at least in the coordinate point, can be expressed as r cosine of an angle, and any y value can be expressed as r sine of theta. Tangent is y over x, and r squared equals x squared plus y squared. So remember, this is kind of like our tools whenever we do want to convert equations between polar and rectangular and vice versa. So let's do a couple more examples. We'll start by looking at example 1, or activity number 1. Notice what we're doing here. We want to go from rectangular to polar. So we want to have a rectangular function, and we want to convert it into polar. So let's concentrate on example A. Our task is to get rid of the x's and the y's and make them equal to r and theta. Before we do that, I want to pay attention to this expression here, x minus 3 to the second, and I'm going to expand it because it's just easier whenever we do expand expressions. So after the expansion, you will distribute, that's x squared minus 6x plus 9 plus y squared equals 9. Okay, we still want to simplify this a little further. Notice that in this case, the 9's will cancel out. Because if you take away 9 here, and you take away 9 here, they go away. So now we do have the expression. And I'm going to rearrange my values. So instead of writing as x squared minus 6x plus y squared, I'm going to write them as x squared minus 6x equals 0. It's the same. I'm just rearrange the x's and the y. I place them first. I think I'm missing the y here. So let me fix that. So we have x squared, and I'm going to put the y squared next, then 6x, and that's equals to 9. All right, so now that we have it in this form, we need to start thinking about how can we rewrite this in terms of r and theta. Well, the first thing that I notice is that I have x squared plus y squared, and we have shown that this is equivalent to just r squared. And in addition to that, we also have an x, and we know that x can be represented as r cosine of theta. Now, notice that here we have different r values. So we have an r value in one term, and we have an r value in the second term. And again, the standard form for our polar equations should always be in the form of r equals some expression. So what we do when we have cases of this form? Well, if we have cases of this form, notice that since they have an r in common, I'm going to factor in an r. And if we factor in an r, we're going to end up with this following expression. Distribute r squared, distribute 6x cosine. Now, we're going to apply the rules, which the rule of multiplication, which says if you have two expressions and if they're multiplying and they're equal to 0, that's the same as saying I'm going to get the outer expression and set it equal to 0. And I'm going to get the inner expression and set it equal to 0 as well. And I notice that I have one equation here, r equals 0. So that's one of my solutions. And now, on my second expression, I want to solve for r. So if I want to solve for r, notice that if I add 6 theta, or 6 cosine of theta on both sides, that cancels out. So now I have two equations, r equals 0 and r equals 6 cosine of theta. So there are two possible solutions for this, either r equals 0 or r equals 6 cosine of theta. Now, even though we have two solutions, all this is saying is, here, this is a point. This is literally just a point at the origin. When r equals 0, we're just plugging in a point, and we're saying, look, give me a point that is 0 units away from the origin. So this is just the point at the origin. Now, in some sense, this is the actual equation that we'll be using to represent the given function. Because if we graph them, so let's go to our Desmos activity here. We have our Desmos. Notice that the point r equals 0. It's literally just a point at the origin. That's all it is. It's just a point at the origin. But if we graph the function that we were given initially, notice that this is just some kind of a ellipse, moving certain units to the right hand side. I'm sorry, this is a circle, 3 units to move to the right hand side. And then if we graph our result, 6 cosine of theta, notice that they match. Let's do one more example. Let's take a look at example C. Look at example C now. Same idea. Here we have a Cartesian graph. So let's put it into polar formats. Well, I know that y, that's r sine. And I know that x, that's r cosine, plus 2. Remember that our objective is to write in terms of r equals something. So whatever terms have an r, let's just move it all to the right hand side, to the left hand side. So let's move this 3r cosine, 3r cosine. That cancels out. So now we have r sine minus 3r cosine equals 2. Again, we want to just isolate the r. Notice that in those two terms, they have an r in common, so we can factor in r. So now we're just going to have sine minus 3 cosine equals 2. And if we want to solve for r, we're just going to have to divide by the expression here. Now this goes away. And now we just have an r isolated. So our final result is just going to be minus 3 cosine. So the equation, or the line 3x plus 2, it should be equivalent to the polar coordinate function of 2 over sine minus 3 cosine. So let's do 2 more examples when we go the opposite way. So what if we have an equation that is given to us in polar, and now we want to write it in Cartesian? So let's take a look at some examples here. Let's take a look at A, since it does have the double identity expression. We're going to be taking a look at example A. Again, every single term that has an r or a theta should go away. Well, the first thing that I do recognize right away is that I do have a double angle identity. So let's just rewrite this as a single angle. So recall that sine 2 of theta, that's equivalent to 2 sine cosine of theta. This is just a double angle identity. And the same idea, notice that here we're missing an r in front of the sine, and here we're missing an r in front of the cosine. Because once we have those r either in front of sine and cosine, we can represent r sine as y and r cosine as x. So since we're missing 2 r's, I'm going to multiply both sides by r squared. Now we're going to have r to the fourth equals 2. One of those r, I'm just going to put it in front of the sine. And the second r, I'm going to put it right in front of the cosine. Because even though we're multiplying r squared, recall that r squared is equal to r times r. So 4x times r squared, that can also be seen as 4 times x times r times r. Since they're all multiplying, then I can just play around. Because here they're all multiplying. It's 2 times r times sine times r times cosine. They're all multiplying, so I can play around with the location of those multiplication. So now that I have this, notice that I have kind of like what I wanted. Because now I have r sine, well, that's equivalent to y, and r cosine, which is equivalent to x. So the only thing that we're missing here is r to the fourth. So we somehow have to get rid of this r to the fourth. Well, recall that r to the fourth, that's r squared to the second, where we do have an expression for r to the second. Because recall that r to the second is x squared plus y squared. So therefore, this expression right here, this is equivalent to x squared plus y squared all to the second, because r squared is equivalent to this expression, to yx. And now it's going to be very difficult for us to solve for y, so we're just going to set it equal to 0. So here it is. The original equation, r squared equals sine of 2 theta, that's equivalent to this Cartesian plane equation, or this quadratic equation, or rectangular equation, I should say. Lastly, let's take a look at another double angle identity. So let's take a look at example E. Again, we want to get rid of this double angle identity, but notice that we don't have such an expression as a double angle identity for cosecant. We only saw double angle identities for sine and cosine and tangent. But I know that cosecant, it's equivalent to 1 over sine. So therefore, cosecant 2 theta is 1 over sine of 2 theta. So let me just rewrite this. This is equal to just 8 over sine of 2 theta. So now let's just rewrite our sine function, the double, because we know. So now, if we recall that the double angle identity for sine, that's 2 sine, cosine. So now what we do now is, well, notice there's a lot of things that we can do with this expression, but I can see that I can just perform a cross multiplication. So let me get rid of the fraction, and let's just play around with some linear expressions here. So now we're going to have r times the whole function, 2 sine cosine, equals to 8. And now here notice that this r is just multiplying to the whole expression. So perhaps I can just rewrite it as 2r sine of theta cosine of theta equals 8. And at least this works out, because I have this expression r sine. I can just substitute this with an y. But notice that for cosine, we're missing an r, because we're missing an r, so I can just set it equal to just be the value of x. So since we're missing that r, what we're going to be doing now is I'm going to multiply r to both sides. And by multiplying r to both sides, now I have 2r sine times r cosine. Because even though this r, it's not like this r just gets multiplied to the first. R is multiplying to the whole expression. But inside this expression, everything was multiplied. So I can just put the r whatever I wanted. I could have put in front of the 2 or the r or the cosine, but I wanted to put in front of the cosine. So I do have the expression that is needed. So now notice I have kind of like what I wanted, because r sine is just y and r cosine is just x. So we're almost done, because the only thing that we need to get rid of is r. But we do have an expression for that. I know that I have this expression, r squared equals x squared plus y squared. So therefore r, if I take the square root on both sides, it's equivalent to the square root of x squared plus y squared. So therefore, if I go back to my function, now I can substitute this r. So now we have 2yx equals 8 times the square root of x squared plus y squared. Let's just simplify this. 2xy equals 8 square root of x squared plus y squared. All right. So notice that at this point, we want to see, well, How can I rewrite this? Let's just polish our result. Let's just make it a little bit nicer. Let's start by dividing both sides by 2, because then about this way, this 2 will cancel out, and now I'm just going to have a 4. So right now I'm just looking for ways to make my result a little bit nicer. Let's get rid of this root. So I can do that by taking the second exponent to both sides. So now I'm going to have y squared x squared. Well, 4 to the second, that's 16. And the square root will cancel out with this. So we got 16 times x squared plus y squared. So what do we have now? So let's just rewrite this. Y squared x squared equals 16 x squared plus 16 y squared. So I want to get rid of, I want to write inside the form. So let me get rid of this y to the second. Let's just continue it down here. I think this example become a little more tedious than what I originally intended. So x squared equals 16x squared. So that'll be 15 y squared. Let's solve for y. So therefore, I want to get rid of the negative 16x squared. So now we have 15y squared is equals to negative 15x squared divided by 15. So y squared is equals to negative x squared. Oops. I just noticed that I did a small mistake here. So everything that is in here is completely wrong, because notice that here I subtracted a y square, thinking that it was 2 terms, but no, they're multiplying. So there's no way that we could subtract that y square there. So let me just fix my error here real quick. So we're just going to continue it here. The way that I'm going to tackle this is I'm going to take away 16 y squared on both sides. So now I have y squared x squared minus 16y squared is equals to 16x squared. Now notice that in these 2 terms, I have a y squared in common. So I can just factor that out. So let's divide x squared minus 16 on both sides. We're almost done, I promise you that. So lastly, we have the following. When I solve for y, so there it is. After doing all this work, we finally come up with the conclusion, which is it is equivalent to just 16x squared all over x squared minus 16. A lot of work, yes. But the idea, the most of the tedious part about examples of this form is just the algebraic manipulation. But this is what I wanted for you. At least if you got it up to this point, that's okay. Because notice that at this point, we got everything in terms of x's and y, which is a Cartesian coordinate. But it's just the simplification just to make our expression a little bit nicer. And if we want to still be a little bit nicer, notice that here we have to place a small restriction where x cannot be 4. Because if x is 4, we got 4 to the second, which is 16. 16 minus 16, that's 0. And we cannot have 0 on the denominator.